Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with acid-base titration, and we'll be explaining to you how a titration is done, and also to teach you how to do calculations involving titration of a monoprotic base with a monoprotic acid, titration of a monoprotic base with a diprotic acid, titration involving a diprotic base with a diprotic acid, and titration of a carbonate solution with a monoprotic acid. What really is a acid-base titration? Okay. Suppose that a bottle containing hydrochloric acid has lost its label and its concentration is to be determined. What technique could be used to achieve this? The technique that is commonly used is called titration. In this procedure, a substance to be analyzed, hydrochloric acid in this case, is reacted with a basic solution such as sodium hydroxide of known concentration. This reactant, sodium hydroxide of known concentration, is called a standard solution. A known volume of the acid, called an aliquot, is measured out using a pipette and is poured into an Erlenmeyer flask. The base is placed in a graduated burette and is released gradually, we call it titrated, into the Erlenmeyer flask containing the acid until neutralization just occurs. The substance in the burette, in this case the sodium hydroxide, is called a titrant. To know when complete neutralization occurs, indicators are used. An indicator is a substance that changes color in acids and bases. The following table shows how a few indicators change color when placed in solutions of acids and bases. So here you are. This is a table here that's indicating to you what colors different indicators have in acids and in bases. One of the common ones that we use in here is phenolphthalein. It's colorless in acid and pink in base. Of course, you know litmus, your old friend. It's red in acid, blue in base. Bromothiamine blue is yellow here, blue there. Methyl orange red, yellow, phenol red, yellow. And this what you see in here is a pipette. And the pipette is used to get a sample of the substance that you want to be analyzed. In this case, it is hydrochloric acid. So we talk a little bit more about that pipette. Let's talk a little bit more about the burette. You have different sizes of burettes. And you can see that the burette is graduated. That means any reading of the titrant inside there can be read off from the numbers that you see there, depending on where the meniscus is. We'll talk a little bit more about that later on. So that's the burette. Is placed on a stand here. First of all, before you do a titration, you want to make sure that your burette is clean. You don't know what somebody else used it before for and didn't clean it properly. So normally what we do, the solution that we will be titrating with is used to clean this burette. To clean this burette, you put a beaker here, an empty beaker here, and using a funnel, we pour some of this sodium hydroxide inside here and let it fall freely through this burette here into the beaker there by opening up this stopcock. Now when that is done, you close the stopcock. With the funnel still there, we gradually pour sodium hydroxide into the burette until it is full. Then you remove your funnel and you zero the burette. This stopcock here regulates the flow of the titrant into the container down here. So that's what we have now. You open this stopcock in such a way that all the excess, you might be having some, when you fill it up, your liquid probably could have gone above the 0 mark there, right? Okay, so we allowed the rest of the fluid to fall down until the meniscus touches the 0 mark here, and that's how we fill the burette. Let's talk a little bit more about this pipette here. You have different sizes of pipettes. You have a 1 milliliter pipette, 5 milliliters, 10 milliliters, 20, depends on what you want to do. In this case, we're using a 10 milliliter pipette. How do you use that? We use this to get a certain volume of the solution that you want to analyze. You can see here this pipette has a bulb here. It's rubber and has a number of valves. So we want to suction some of this acid here into this pipette here. We have 10 milliliters of that. So what you'll do, you press one valve that allows the air to be squeezed out of that bulb. So when the air is squeezed out of the bulb, a suction is created. So when you put the pipette into your liquid air and you squeeze another valve here, it allows the liquid to be suctioned into the pipette there, and then you can release the valve and you have your 10 milliliters of your solution there, in this case, which is hydrochloric acid. Again, like your burette, you have to regulate the amount of fluid inside there such that the meniscus there is just touching the 10 milliliter mark there. Now what do you do now? Empty your 10 milliliter aliquot into one Erlenmeyer flask there. You then take your Erlenmeyer flask and you put it under your burette here. Your Erlenmeyer flask, in this case, will be having 10 milliliters of hydrochloric acid of a known concentration. Before you start titrating now, you have to put an indicator inside here that will indicate to you when the titration is over. In this case, we use phenolphthalein indicator. You put 2 drops of phenolphthalein indicator inside here. Then you will start to titrate. As you gradually release the sodium hydroxide, you will be forming inside here some sodium chloride and water. Gradually, all your HCl will be neutralized by the incoming sodium hydroxide that you're titrating here. We want to know the end point of that titration. That is when all the HCl has just been neutralized by a certain volume of NaOH that we subsequently read off from the burette. Because we started at 0, so if it ended somewhere, we can know what volume was used. So the indicator here will tell us that. You have to keep swirling the solution all the time while you're doing the titration to ensure that there's nice mixing of the sodium hydroxide with the acid there, so you allow the neutralization process to go on. When it's coming towards the end, you'll notice that the pink color will want to persist. And as you keep swirling that, it will disappear. That is telling you your end point is approaching. So what you do, you regulate the stopcock to allow the sodium hydroxide to fall as drops. There comes a point where 1 drop of this sodium hydroxide makes the solution just alkaline enough to change your phenolphthalein from colorless to pink. So you'll end up with a pink solution like that. 1 drop of the sodium hydroxide should change that to pink. So that marks the end point of the titration. Where do we go from there? You see that I have created 4 aliquots here, okay? What happened is that because people do not know to do accurate titrations, for that reason, people do a number of titrations. So some people do 3, so the 4. So you do the same thing here, use the pipette, and you get 4 aliquots of the HCl of a known concentration, but 10 milliliters each. And you repeat the titration a number of times, and you get the different readings. Let us look at a typical titration here and see what readings are obtained. Let us suppose now that in this titration that I'm giving you here, it's very similar to the one that we talked about there, okay? Those are your 10 milliliter aliquots of your HCl of a known concentration, okay? All right. So in the burette, let us suppose that we have 0.1 mole per liter of sodium hydroxide. And these results show you here the burette readings for those 4 different titrations. Let us put it in perspective now. So initially we said you zero the reading of the sodium hydroxide in the burette. So when the meniscus touches 0 there, so initially it was a 0, okay? Then after you finish the first titration, you read off the volume of sodium hydroxide. That is the volume you've used there in the first titration. And you get that by taking 0 and you subtract it from the final reading there for this first titration. And that's the volume of sodium hydroxide you use in the first titration. Now, your second titration is starting at 11. So that becomes your initial reading for the second titration. And you continue with the second aliquot now. You place a second aliquot under your burette and you do a second titration. In the second titration now, it went to 21.5. So you want to know what volume you use. So you take your initial reading for that one, which was 11, and you subtract it from that one there, and you got 10.5 here. So that's the volume there. You're now going to want to do a third one. When you do a third one now, this becomes the initial reading, and that's your final reading for the third one here. Okay? You subtract and you get that, and somebody did a fourth reading. So this one became the initial reading, that's the final reading there, and this is the volume that we've used. Now, how do we go about finding the concentration of your hydrochloric acid? You can see here, when you compare these results here, this one is out by far. So these ones are close to each other. So we'll discard this reading here. And what we'll do now, we'll add these 3 here and take the average of that. And that translates into 0.103 liter. If it's just as if we did one titration, and that is the volume you use to neutralize your 10 milliliters, if you don't want only 10 milliliters of your hydrochloric acid of unknown concentration. So the whole objective of that titration there is to know what volume of sodium hydroxide was used to neutralize 10 milliliters of HCl of unknown concentration, and that's our volume here. Okay, let's see how you calculate the concentration of that acid. We know the concentration of your sodium hydroxide, and we know the average volume that was used. So the number of moles in one titration, so we did the average of all of them, is that number of moles of sodium hydroxide. And this number of moles was necessary to react with your 10 milliliters of your HCl, okay, that you use inside your Erlenmeyer flask. So the next thing you do is you balance an equation between the sodium hydroxide and the hydrochloric acid. This is the given reagent because you've just calculated its number of moles. And you can see it's a 1 mole to 1 mole ratio here. So we do not know this. This is the required number of moles of HCl in that aliquot there. So let's see what number of moles that translates into. You do it given over required 1-to-1 cross multiply, and that's the number of moles of HCl that was in one aliquot. So we know number of moles, but we know the volume. We know the volume of one aliquot, which is 10 milliliters, and that change to liters is this. So 10 milliliters had that number of moles of acid, so your concentration is equal to C is equal to N over V. Okay? And that is how you do a titration. So quick review. The substance that you want to find out about its concentration is poured into these Erlenmeyer flask here. 2 drops of phenolphthalein indicator are placed in each of them. Okay? And then your burette is prepared with the sodium hydroxide. In that case, it is called a titrant. That's a standard solution. You know the concentration of that. You choose whatever concentration you want because you suspected that this HCl was probably about 0.1 mole. You're not certain about that. Okay? You're not certain about that. You believe that it was 0.1 mole. So you have to get a concentration of sodium hydroxide that was similar to that. Okay? That's why you choose 0.100 mole per liter. So you do 4 titrations. And in the end, you put all of that in a table and then look for any disparity in the results. This one doesn't look too well. That maybe person is nervous, and then they get 3 nice results there. What do? You add them together, you find the volume, and they change that to liters. Now that you know the concentration of that sodium hydroxide there, you can know how much was used in one titration. N is equal to C times V. That's the number of mole of sodium hydroxide that is required to neutralize 1 aliquot of your HCl. You want to know how many moles of your HCl in that aliquot, balance an equation, show the mole ratio, and that becomes the required quantity. That's a given one there. You find for X. X is equal to that number of moles of HCl in that one aliquot. Then knowing the number of moles, you know the volume was 10 milliliters, which is equal to that number of liters. That's your concentration. Same principle will be used in all of these here. So here again, we're using sodium hydroxide as a titrant. And look, you're using 20 milliliter aliquot of sulfuric acid. And you want to calculate the concentration of the sulfuric acid. Okay. So when you do your subtraction there, you'll end up with these values here. Sorry about the mix up there. And here you can see this one is out. We discard that one. And we use these 3 here to find the average volume. See? You find the average volume here. Knowing the volume and the concentration, which is 0.1 mole per liter, we can find the amount of sodium hydroxide here, N is equal to C times V, that's required to react with 1 aliquot of sulfuric acid of volume 20 milliliters in this case. So you want to know the amount of sulfuric acid in that 20 milliliter aliquot, right? So this is given again, and that's required. You do a balance equation there. Now you're seeing that there's 2 moles of that, required 1 mole of that for complete neutralization. And then you do your given over required. Your given is the sodium hydroxide, but it's 2 to 1 now based on that equation there. When you do your cross multiplication, 2x is equal to that, x is equal to that number of moles of sulfuric acid. Now you know the number of moles, and we know its volume, which is 20 milliliters. That translated into that. You find the concentration is equal to C is equal to N over V. And that's the concentration of your sulfuric acid. All right. Now you titrate a diprotic acid with a diprotic base. The diprotic base is barium hydroxide now. And that's the concentration of it in the burette. And you take it 10 milliliter aliquots of sulfuric acid. Okay, in your Erlenmeyer flask, and this is going to be a burette, and you titrate that. Alright. So here again, you're seeing the values here. These are the 4 values here. Inspections show that this one is a little bit out. Normally people do a trial run to see where the value might be. So we're not taking that run there. Nothing is wrong. We take these 3 runs here. Okay, and then we take an average of that. And we get that volume of, then what do we do? Find number of moles of barium hydroxide. N is equal to C times V. Okay, we knew that was the concentration of the barium hydroxide, and we had to find what volume was used to neutralize a 10 milliliter aliquot of sulfuric acid. And that's the number of moles of barium hydroxide that was used. And you now do your equation to see how they react. You can see 1 mole of that requires 1 mole of this for complete neutralization. So your mole ratio is 1 to 1, and then X is equal to that number of moles of sulfuric acid in that 10 milliliter aliquot. And your concentration is equal to N over V divided by volume there. Okay, and you get your concentration of your sulfuric acid to be this. Titrating a monoprotic acid with a solution of a carbonate, all right? So your aliquots will be 10 milliliter HCl of unknown concentration, won't know what that is, and your solution in the burette will be equal to 0.200 moles per liter sodium carbonate. And that is reacting with the HCl inside your Erlenmeyer flask. And these are the results that you have here. Again, the trial run is there. You take it off and use these three here. Alright? People do a trial run to see where the reading might be, okay? So your average volume of sodium carbonate you use is found by adding those three here and divide by 3, and it's 20.4 milliliters. And divide that, of course, by 1,000 to get its volume in liters. See, divided by that, you get that's the volume in liters. Number of moles of sodium carbonate used is equal to C times V, and you get that number of moles there. Balancing equation of the reaction between sodium carbonate and HCl to find your mole ratios. In this case now, you're given this because we know its number of moles. You can see 1 mole of this is requiring 2 moles of that for complete mineralization. Supposed to get some carbon dioxide coming out here. Okay. Yes. That's why you're going to see it's going to be effervescent. Oh, that's supposed to be up there. Sorry about that. So it's 1 to 2. So the given here is your sodium carbonate, which is 1 mole, the 2 moles of the unknown there, or required one, hydrochloric acid. Do your math there. And X works out to be that number of moles of hydrochloric acid that is contained in your aliquot. Find its concentration by using this formula here. C is equal to N over V, that's number of moles. And this is your 10 milliliter aliquot that translates into that volume for liters. And that is the concentration of your HCl here. Alright. These are some problems here for you to solve. You have 3 of them there. These are found in your solution manual. The answers and everything. So you can go about doing those. Alright, so quickly then, quick review of that. So you have a bottle that has lost its label of HCl, and you suspected that it was 0.100 mole per liter. And you wanted to verify this. Take a 10 milliliter pipette and get 4 aliquots of that inside 4 Erlenmeyer flasks. Inside that, each you put 2 drops of phenolphthalein indicator, right? And then you fill your burette up with a standard solution. Let's call it titrant. You'll have to know what is the concentration of that solution. In this case, we're going to make it one similar to the one they suspected lost its label of 0.1. Okay, so that we can have some nice values in the burette there. Then what do? You fill your burette with that. As you titrate the base into the acid, gradually a salt and water is formed here little by little. Yes, so the concentration or the amount of HCl gets lessened as you titrate more and more of the base inside here, until at one point you have only salt and water inside here. 1 drop extra of that thing there can change this whole thing to pink, because your phenolphthalein indicator was colorless all the time, and 1 drop of that turns it to pink. You do that to a number of times to get an accurate reading. Your fourth one sometimes is a trial run. 3 you do accurate, and you get these values here. So when you get these here, you find the average of these to get the average volume of your sodium hydroxide of that concentration that you're using. Then this leads you on to finding its number of moles. So this is the volume here using the formula N is equal to C times V. You found number of moles, okay? So that's the number of moles of sodium hydroxide that was used to neutralize whatever amount of HCl was inside that 10 milliliter aliquot that you had in the Erlenmeyer flask. Balancing equation to show mole ratio between the sodium hydroxide and the HCl, you see it's a 1 mole to 1 mole. This is given, this is required. Set up your mole ratio there put in the given one that you just calculated, let x be the one that you're looking for, okay? And you found that that was the number of moles of HCl in one aliquot. You take that and divide by volume for one aliquot, and that is where you go for. Sometimes you can have different mole ratios, and you'll know how to balance the equation. So your given over your required can be 1 to 2, 2 to 1, and stuff like that. In all cases, you find for x, that gives you a number of moles of substance in your aliquot, and then divide by the volume. I hope that was helpful. If you actually perform this, then you'll get the essence of it. So see you again next time, and